Hello and welcome to Answer Everywhere. Today we're taking a look at XLA, a machine learning compiler for GPUs, CPUs, and machine learning accelerators. I don't know really what this is going to be up to. My guess is it's essentially compiling, taking things written possibly in stuff like Python, compiling it down to fast, mostly linear algebra routines, probably like matrix multiplication primarily, and dot products, which is just matrix multiplication, to be accelerated. And we see it's mostly C++, 88.8%, MLIR, I don't know what that is, Starlark is the build system, some C, whatever Smarty is, and a little bit of Python. Python, I'm going to guess, is mainly around like testing, although there might be some initial Python support, and then other tools, like if we look down here, we see that PyTorch, TensorFlow, and JAX might have bridges to the XLA framework. PyTorch on XLA devices. Okay, MLIR. This is just showing me the MLIR code. All right, so MLIR is a framework for compiler development. A unifying framework, MLIR can make optimal use of a variety of computing platforms such as GPUs, DPUs, TPUs, FPGAs, AI ASICs, and quantum computer systems. It's a subproject of LLVM compiler infrastructure. I think somebody may have requested that I look at this, the MLIR repo. This sounds familiar, but we're not doing that today. Today we are taking a look at the XLA stuff. All right, so where do we start? Okay, so we do see linear algebra in the name. Who is? Let's see if we can figure out who OpenXLA is. We get nothing there. And then we'll look up OpenXLA XLA on Google. There's a singer named XLA. Library developed by Google. No. Advanced optimization framework within TensorFlow, which is a Google thing. And I'm wondering if this is ultimately a Google initiative. That's really what I want to know. Much knowledge is required for maths for machine learning. I think that's true, although a lot of it at the end of the day ends up being linear algebra. Hello, wealthy mindset frame. So I just want to see who's involved in this. Industry partners. I have a feeling this came ultimately from Google. I guess it doesn't matter. You see Bert. Today, we're taking a significant step towards eliminating these barriers by making the OpenXLA project. Okay, so this does seem to be from Google. This is from Google's blog. That just helps me a little bit to orient me, because I have more of a sense of how Google thinks than other organizations. And they have Kokoro here, which should have been a giveaway. Okay, so here's the XLA directory. What do we expect to see? We expect to see lots of linear algebra. I don't know what the hard part here is. We've seen about 8 billion different linear algebra routines, or not linear algebra libraries that run on GPUs, but like for example in game systems. But this is not that. This is something else. There are presumably different trade-offs. It's unclear like how different they are. By unclear, I mean unclear to me, just because I don't know much about computation in terms of either like the GPU hardware model or what the needs of AI are currently. So I don't really know how those are expected to differ, and I also don't know like, is this better than using like LAPACK or BLAST or any of the other optimized libraries? I don't even know if those run on GPUs. So we'll try to find some of that out, but these are some of the things going through my head. What I do know about at least a lot of the LLM stuff, the original papers for things like attention is all you need. Everything is essentially a dot product or a matrix multiplication. So there's not a lot of super different operations. Everything looks pretty linear. And if I understand correctly, I think at least the original idea, or one of the ideas of the tensor processing units, was that you compared to a regular GPU, machine learning applications can sacrifice precision. So you might be able to get away with using int32s for machine learning applications, whereas GPUs might work with like int64s, and by having the kind of lower resolution baked into the silicon, you get some performance advantages. So I don't know if that's 100% true. I think that's more or less directionally true. If it's not, please let me know. I want to learn, so I'm looking at chat. I want to learn machine learning within 1 to 4 months. I already know programming, Python, and high school math. I'm currently learning linear algebra. Is my goal achievable? I would say I don't know, because I don't know what it means to learn machine learning. It's not a specific enough goal, and I would argue, there are professors of machine learning who do nothing but read papers and go to conferences and teach classes all day, and I would say not any one of them like knows machine learning, like all there is to machine learning. So you kind of have to have a more of a sense. You have to have like more of a specific goal. But if you want to understand, for example, most of the math behind a specific paper, or like the most popular kinds of things, then I think that in 1 to 4 months, if you're working through a linear algebra textbook for like engineers, then you'll get a long way there. And the closer you get, the further along you get, the more you'll have a sense of what you don't know. And then once you know what you don't know, you'll be able to say, well, this stuff over here, I don't really actually care about learning. Mainly becoming an engineer, that I don't know. That depends on a lot of stuff that I don't have access to, such as what what recruiters are looking for. That's a good question. I just don't have that information, unfortunately. But I think you'll be able to understand stuff and start working with it. Okay. So I was going to ask, tell me about the the XLA. Oops. Oh, no. Oh dear. Okay. Sorry. My hands are hurting a little bit, and so I keep hitting the wrong keys. So I'll say there's an XLA machine learning accelerator. If I understand correctly, can I do text typing? Let's try this. I think I've tried this before and it worked. Hello. Okay. Let's try this, because I'm reading it a lot anyway. There's an XLA machine learning. Let's try one more time. There's an XLA machine learning library that optimizes linear algebra routines for running on machine learning accelerators, as in hardware devices. Period. There's also a large number of physics and game engines that have optimized linear algebra routines that run on GPUs. Period. Give me an overview of how the design goals of XLA differ from the design goals of a game engine when it comes to optimized linear algebra, period. And I'll just edit this. And so, one of it might be that like games just really only care about up to 4-dimensional matrices. So it'll probably take a minute to think about this. While I was thinking about this, I want to look up LabPack, let's say GPU. BLAST doesn't include eigenvalue solvers. And how is LabPack different? I don't know what the difference between LabPass and BLAST are. So LabPack is the linear algebra package for a standard software library for numerical linear algebra, solving routines for solving systems of linear equations, least squares, eigenvalue problems, etc., matrix factorizations. Originally written in Fortran, but has moved to Fortran 90. And then BLAST is BLAST a standard? No, it's a library. They are the de facto standard for low-level routines for linear algebra. Have bindings for both C and Fortran. LabPack is a higher-level linear algebra library built upon BLAST. So LabPack has BLAST as a dependency. What about GPU? Llama, the library of accelerated math applications. This is different from the double L Llama AI thing, but has some support, I guess, for GPUs. All right, let's see what Gemini is saying. Have I used the GPT-2 model? Do you mean GPT-4? So far, I've only used GPT 3.5. All right, so here's an overview of the design goals of XLA. They differ from a game engine. So XLA TensorFlow focuses on machine learning workloads. Goals are maximum performance. It prioritizes achieving the highest possible throughput for machine learning workloads. It heavily analyzes computations and generates machine code tailored for specific ML algorithms. Flexibility. While XLA targets ML workloads, it offers some level of flexibility to handle different blah, blah, blah. So trade-offs, generality may not be as general purpose as linear algebra libraries and game engines. It may require more work to adapt non-standard ML operations, and the heavy optimization for specific hardware can increase development and maintenance costs for the XLA compiler. So the game engine is more focused on real time. There's a balance between performance and efficiency. That makes sense. And then trade-offs, peak performance. So game libraries may not achieve the absolute best performance in specific ML algorithms compared to XLA specialization. Okay. So that makes sense. Game engines, it's important to get the pixels onto the screen when you need them to be on the screen. Whereas, and to do that, they might sacrifice some things, including performance or, I don't know, efficiency. Okay, so here's the root directory in XLA. Are these the same? These are the same. All right, so what do we want to see? I guess we'll look at an array, a 2D array and a 3D array. These should all be about the same. I'm going to spend about like half a second on each. Bitcast, this should be like bit manipulation stuff. Autotuning.proto, this is some protocol buffer. There's some sort of auto-tuning stuff. I'm going to guess that maybe auto-tuning is essential. I don't know what that means. It might be, so tuning something. Tuning what? It could be like maybe a little bit like a hotspot compiler, where it's noticing what sorts of computations you're doing a lot of and making those faster. We have a CPU function runtime, which might be interesting because some compiler macros. Device util EF57. I don't know what that is, but we will look that up. Error spec might be interesting. Execution options. Executable run options is executable options util. Front-end attributes, index util, layout, lazy, presumably for some sort of lazy computation, literal test, overflow. So this must be something like a maybe like an integer overflow utilities. Permutation. I'm guessing permutations are about like combinatorics, like permutations. So I think the real-time thing is a big one. Many XLAs do just-in-time compilation, which improves performance, but becomes less predictable, which sucks for games. Cool. So what do you mean by XLAs? Is XLA the device or the like binding or implementation of this library? So we have protobuf util. Why? I have no idea. Reference util shape. I don't know what shape is. This might be like the shape of a, it might be like a literal shape, like a geometric shape. Or it might be like something like you have some computation that you can parenthesize in different ways. And it might be something like the way of parenthesizing the computation. We also have shape layout and shape tree. That seems a little bit more like geometry. Sharding. Sharding sounds like it's probably maybe going to be like database sharding, where we have some computation and we want to send it to different machines to parallelize it. We have status or. This is looking pretty googly. Some text literal. Union find. This is presumably an implementation of union find, the algorithm, and a window util and XLA. Does XLA have a UI? Okay, accelerated linear algebra. Okay, so is XLA, it sounds like maybe XLA is a general abbreviation that Google is essentially trying to trademark in some sense. And so these are the things that are in the root directory. Let's see if, so we have MLIR, which I'm going to guess is just MLIR support. Is probably something we can mainly ignore. It's going to be like a level down from where we are. But so we have the intermediate representation. Well, why not? We'll open them. We're not going to get through all of this stuff. And we have a client. Experiments. I'm going to guess this is like, okay, so this is for mainly because we don't really have branches. So it's a place to work on code. Examples. Examples, I think, is going to be useful for me. I'll open that in its own window. And hello. What is hello? HLO evaluator? HLO evaluator. I don't know what that is, but we'll look at the, oops, I meant to get the H file. Experimental auto sharding transforms, and then intermediate representation. HLO compiler, let's look at that. Okay, this is some other attempt to do a compiler for both the CPU and the GPU, I think. And it mentions MLIR. The work on MLIR HLO can be seen as a stepping stone towards building TCP. What is TCP? Tensor Compute Primitive. Okay, so there's this MLIR thing, which is, if I understand it correctly, this is it's like an intermediate representation that has some additional information that allows it to be used in compiler, I guess the middle end, where the target can either be the CPU or the GPU. And I think the idea there is probably that we get to use like compiler optimizations on this middle representation independently of like where it's going to go. And so that generalizes the work that we've already done for making an optimizing compiler for the CPU. We can now use it in this new GPU-friendly world. I think that's what the MLIR is about. Let's take just a quick look at it again. A novel approach to building reusable and extensible compiler infrastructure. It aims to address software fragmentation, improve compilation for heterogeneous hardware, significantly reduce the cost of building domain-specific compilers, and aid in connecting existing compilers together. Okay. So who started this? There's a paper from IEEE. Do I only get an abstract? Is IEEE free? I have to sign in. Well, who are the authors? I want to know the authors, though. You can probably grab this. Look in Google Scholar. And there might be a preprint version. University of Waterloo. All right. Yeah, Google, Indian Institute of Science, Google. So I have a feeling this is primarily, MLIR is primarily a Google initiative. All right. Sounds good. So what is Google up to? Google is up to the thing that Google always does, which is they want to have a, they've looked around and have decided that AI compute sucks. And so they're going to build their own hardware and like compilers and all of this stuff and kind of change the way that we think about getting stuff onto the GPU from where it is now, which is a lot of, I think, probably like handwritten CUDA and that sort of thing, or using libraries that import CUDA. Okay, so that's where we are. Or at least I think that's where we are. Here's array.h and array2d. I'm not sure if this is where I want to start, but let's take a quick look at array. Where I want to get to is like the code that's like doing more thinky stuff. Like if there's optimizing code in here as opposed to in the MLIR stuff, I want to kind of see that. But we might as well look at the linear algebra representation as well. All right, so we're importing a bunch of stuff, including algorithm, array, cstdint, maybe cstring dint. I don't know what that means. Something maybe converting to integers or something. This looks like pretty googly C code. We have a template. Enable if t. Is this C++? This has to be C++, right? I don't think there's a, yeah, C++. Okay. All right, so we have whatever enable if t is specialized floating point v t is same. Okay, I don't know what this is. This is some template doing some sort of computation about floating points and whether they're the same. We have a type trait that is valid when all elements in a parameter pack are of integral type. So I guess integers, not using an alias template to work around MSVC 14.00 bug. Visual Studio Code, I guess. All right. And we have a general n-dimensional array class with arbitrary value type. And it's a template. So it's templatized by some type. It's an array. We've got some standard array accessor methods and stuff, I would imagine. We've got these initializers for up to 4 dimensions. Type inference can have a hard time parsing very deep initializer list nests, especially if one or more dimensions is 1 as the compiler just sees a single element integer initializer. These type defs allow casting explicitly with less typing. Okay, and so we have this array. You pass in an abscel span of sizes. I don't know what an abscel span is. I think it's just like some span of memory. It's like a string view, right? But for non-strings. A type for holding a reference to existing array data. Okay, so it's like maybe like a slice. The span object, much like a string view object, does not own the data itself. The data being referenced by the span must outlive the span itself. Unlike view type references, a span can hold a reference to mutable data. Okay, so it's kind of like a slice of an array of sizes. And you can create a 2D array from a nested initializer, blah, blah, blah. And this is just array stuff. Fill IOTA fills the array with sequentially increasing values. Seems nice to have. Fill random uniform. Yeah. Fills the array with random uniform variables. So this seems like a good API. Okay, here's array 2D. This is maybe something that we imported from the other array. I think CST_dint is an advanced int types. Okay. C standard int. That must be how that's supposed to be. Yeah. Okay. That makes sense. Thank you. Linux 48. So array 2D should be more specialized than array, except we're going to do 2D things. We should probably still parameterize by type as we are here. I'm going to assume the same for 3D and 4D. I don't know if we can go above 4D, but it seems like array tells me it's general. Oh, whatever. It says general, right? And how high can n go? Seems like you can pass in any list of sizes, really. All right. So bitcast is going to do what? Bitcast is an extension of standard bitcast, absol bitcast. Whereas those functions require trivially copyable source and destination types, the present function template may be specialized for additional types that do not satisfy that triviality property, but that have alternative ways for accessing their underlying representation. Okay. Concretely, we provide specializations for the custom floating point types, eigenhalf and TSL bfloat16. Eigenhalf. I'm curious what that is. Those types are effectively stored as a sequence of bits, but the classes are not trivially copyable. Okay, so I think that what's going on is that bitcast is like for casting things that are sequences of bits, and eigenhalf and TSL bfloat have that property, but I don't know in what sense they're not trivially copyable. I guess when you copy one from another, you might need to monkey around with the bits a little bit to maybe some bits have semantic meaning, and when you cast them, those semantic meanings change or something along those lines. So bitcast is some template. You pass it in I don't know why it's called U, but you pass in some, oh no, sorry, it's called U because it's the second type here. You pass in some source bit thingy. You do some static asserts about the sizes. And we would like to check if standard is trivially copyable here, but there's no reliable implementation available to us. And we're just going to call abscel bitcast. So what? So if we call capital B, capital C bitcast, and the sizes are the same, it seems like we just call the underlying abscel bitcast. I don't know how that helps us, but we've got the other version, which has some inlining. And I guess, oh, I see. So I think this is saying that if T and U are both unspecified, then we fall back. And here, I'm not sure that I've ever seen a template with no templatizing, but I guess this is saying that we've specified that the output is a bfloat 16. The first input is a oh no. What? So it's a UN16 source, and I guess you're going to get a bfloat 16 out. And to do that, we're going to call eigen numxt bitcast, kind of deferring to this eigen numx thing. And similarly, and so on. And I guess that what this syntax must mean is that we have to say it's a template, but at this level of generality, there's no like unbound variables, because this is a template call, and this variable is bound here, or something along those lines. But why can't we just call inline here? I'll ask the AIs. Do I understand the purpose of this XLA? Instead of implementing custom kernel for each layer, you implement CUDA code for basic math operations and a mechanism that generates a big kernel. Big kernels by combining the primitive kernels. I don't know. I don't think we've gotten there yet. Implementing it. Something like that. So I think we're ultimately going to compile to like MLIR, and then MLIR is presumably going to compile to something like CUDA. So I think there's like maybe a step in between what you're talking about and where we are. Tell me about this syntax here in particular. What's up with the empty brackets? Why can't we just inline the call to the templated function? Question mark. That wasn't terrible, but this is wrong. It provides a function template called bitcast that casts a value of type UN16 to a, yeah. This line declares an explicit specialization of a template. Okay. So this is just saying this is specializing a template. I guess that has a syntax. It's not so surprising that it has a syntax. Indicate that we're calling the specialized version of the template function. All right, great. And then it'll ask, well, maybe, let's see if we can find MLIR targets. Can I like do a search here? How about does, yeah, MLIR is like a plugin or something for LLVM. And I'm not sure what the right word is, but it's like an intermediate representation for LLVM. I don't know how exactly that works, but it's somehow connected. I guess maybe LLVM can just use different intermediate representations. MLIR must stand for Machine Learning Intermediate Representation. How to generate CUDA bin from MLIR. I was trying to make a GPU compilation program, pipeline, but could not make it work, blah, 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 blah. I then tried to compile. You need some form of host code to actually launch any kernels on the device. However, if you just want to call some arbitrary GPU function, you could link your created binary. Does MLIR compile to CUDA? Okay, so ChatGPT says that we can use MLIR to compile to CUDA. It does not directly compile to CUDA. Instead, it provides the necessary infrastructure and tools to build custom compilers or translation passes that target CUDA. And then I'll ask Gemini the same thing. I feel like Gemini is maybe copying ChatGPT somehow. So there's a CUDA LLVM compiler. Maybe that's the thing that I'm missing. It's based on the widely blah, blah, blah. Add GPU acceleration. So somehow you connect up the different ends of the compiler, the middle end, and the end, the last end, whatever that's called. And I think through some combination of MLIR and the NVIDIA CUDA compiler, you can compile to CUDA. I don't know how it works for AMD. I know AMD has this ROCm thing. I don't know if that just runs CUDA code or if there's something else going on in between, but somewhere along those lines, you can do all that stuff. Here's autotuning.proto. This should be some proto that describes autotuning. I'm hoping this is going to tell us a little bit about the magic of XLA, although it may not. It may just be like performance statistics or whatever. This file defines protos that store the results of auto-tuning various operations. They are in proto format because we want to log them structured. They offer tremendous statistical testing and debugging value. Okay, so the Google logging infrastructure eats protos, so protos are here. We have things like the version, the compute capability, major and minor, auto-tune result, which I guess might have a failure, like red zone modified. The algorithm wrote memory outside of its output buffers. The algorithm might give a different result from the reference algorithm. That's not good. Wrong result. The algorithm was rejected for failing to run for known bugs. And then we have a failure result, which has a failure kind in a message. We have a conv key, legacy and unused. Okay, so it's legacy and unused, but it had an algorithm, which is an int64, and whether tensor operations are enabled. We have a gem key, which has an algorithm, which is an int64. I don't know if we're just essentially giving unique IDs to algorithms or if there's like some mapping to known algorithms. A CUDA conv plan key, which is no longer used. I don't know if conv is like convolution. A Triton gem key. What is gem? I think Triton is maybe one of the TPUs. Is that right? The group gem kernel launches a fixed number of CTA to compute group gems. Thank you. Launch various things with Triton. Triton is a lang. Triton is a language and compiler for parallel programming, a Python-based programming environment. Why gem is at the heart of deep learning. I guess that's gem. Is that gem? This is gem. I guess that's gem with the J. I thought she had a G, but I guess not. All right. But what is it? Here's BLAST. We looked at BLAST earlier. So-called gems. It's part of the BLAST basic linear algebra subprograms library that was first created in 1979. And until I started trying to optimize neural networks, I'd never heard of it. And to explain why, here's a diagram from Yangqing Ji's thesis. So we have some GPU forward time distribution and a CPU forward time distribution. I don't know what forward time distribution means. And I don't know what conv, pool, norm, or any of this stuff is. Okay, it stands for general matrix to matrix multiplication. Just tell me what the thing is. It's just matrix multiplication, right? I'll add this to Wallabag so I can read it later. But let's look this up. So I'll pull a few of these and just add them to Wallabag. So next time we come across them, I'll know a little bit about them. But something about matrix multiplication. Let's look at the NVIDIA one real quick. A fundamental building block. For many operations in neural networks, for example, fully connected layers, recurrent layers such as RNNs, blah, 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 blah. What's the, I want the API. Here's a diagram. We have an A matrix, a B matrix, and a C matrix, a K tile, an M tile, an N tile. And I think it's just saying that we're doing matrices block by block. As we discussed in GPU architecture fundamentals, the latest NVIDIA GPUs have introduced tensor cores to maximize the speed of tensor multiplies. Sounds like they're starting to compete with tensor units. As they should, I guess. All right, so something about multiplying matrices. Let's see if we can find the BLAST like API reference. I just want to know, is it literally just you pass in two matrices and get a third out? The gem computes a scalar matrix product and adds the result to a scalar matrix product with general matrices. The operation is defined as the output C, I guess is how what this notation is indicating, is alpha. Alpha is probably a scalar times op of A times op of B plus beta times C, where op x is one of the identity function op x equals x, or the transpose function, or the h power, which I'm going to guess is maybe the complex conjugate. And then alpha and beta are scalars. ABC are matrices. And okay. So we've transposed. So now I'm curious about what this is. I'm guessing it's like the Hermitian. I don't know. There may be something linear algebra I'm forgetting. Okay, so that's what the gem is. In the case where we're not transposing or hing, then this is just alpha A times B. We're taking A, B, multiplying them, scaling them. Alpha could be 1, in which case it's just the matrix product. And if beta is 0, then it's just the output is the matrix product of A and B. I don't know why C is both here and here. Perhaps we rewrite into C. And in general, we might add we might take the matrix product, scale it by alpha, and add it to some scaled version of C. Or something along those lines. All right, so that's what a gem is. Back to the autotuning proto. We have an autotuning log, which is going to be just the log statement. Okay, so this is mainly like logging, although that was a little bit interesting. We got down the gem rabbit hole. Here's CPU function runtime. You got an encoded buffer info, packed kind and size, entry param number, buffer info class, stores information about one buffer used by an XLA CPU compiled function. These buffers are used for holding inputs to the computation, outputs from the computation, and as temporary scratch space. So we have some buffers. And this is for running on the CPU, I guess. And the CPU is kind of like the not really what we care about. We mainly care about the GPU, right? Although I think I read that that Google uses maybe CPUs for inference. In some cases, it's like more cheaper or better than GPUs for some things. I don't remember the details. Maybe it can also be compiled to PTX, which is potentially. I honestly don't know anything about the hardware side. So any of that is possible as far as I'm concerned. We can encode stuff. Encodes this buffer info into two 64-bit integers that can be used to reconstruct the buffer info later using the constructor. So I'm not really sure what this is. We're kind of encoding buffers and unpacking them and maybe like serializing them. We can align some stuff, align to 64 bytes to mimic TSL, allocator, K-allocator alignment, malloc, continuous buffers, and so on and so forth. We don't need to see the implementations of that. Compiler macros, I kind of just wanted to see if there's anything that like will tell us about the magic, and not really. It seems to like stuff like unroll and some other stuff. ELF57, I have no idea what this is. Utility function to split a double precision float into a pair of F32s. So this is like float stuff. I guess F64 to F57. What is 57 though? Is this like from a standard that was written in 1957? ELF power. Let's try floating point 57. There's IEEE 75.4. FP64 or float 64. I think this is something about this stuff. I don't really know. Using Starbend's lemma, if A and B are two positive floating point numbers, and the half of A is less than or equal to B, which is less than or equal to twice A, then their differences can be computed exactly. Okay, here's error spec. This is just going to tell us about how we're thinking about errors. Structure describing permissible, absolute, and relative error bounds. Okay, so we're kind of bounding errors in a way that presumably the algorithm can reason about. So AABs, A rel, maybe A relative is 0, relaxed nans is false, and I guess we're taking the absolute value, the rel of A rel, and relaxed is being set with the relaxed. I don't know why we've gone from AABS to just regular ABS. So ABS is absolute error bound. Oh, I guess because ABS might be absolute value. I don't know. The absolute and relative error bounds. If relaxed nans is true, then any result is valid if we are expecting nans. In fact, this allows the tested operation to produce incorrect results for inputs outside its mathematical domain. And all nans are equivalent is by default true. Then we don't check the bitwise equality of nans. All nans are considered equivalent. And fewer infs is okay. Set the false. If this is true, then we treat each plus or minus inf in the actual result as equivalent to our choice of either plus or minus inf in the min-max floating point value. If the expected result is plus or minus inf, the actual result must still be plus or minus inf. In effect, this allows the tested operation to overflow, so long as it's overflowing on large values. All right. Here's executable run options. I'm going to guess this is not so exciting. We have what? GPU executable run options. We have things like a class of run IDs, a callback, this thing then execute function, callback used by the GPU backend and by the GPU backend only. This is a one-sided version of then do host callback that enqueues a callback onto a stream. This is kind of like the async then functionality, it looks like. We can send device memory, run options, etc., executable options. All of that's fine. I'm going to ignore options util. Lazy should be some sort of lazy computation. Lazy takes an absol any invocable. I guess that's a thing that you can call like a function. And it returns a maybe value. which moves the result of its function. And I guess just encapsulating it in this lazy allows you to like invoke the thing later, maybe by calling get. Which it seems to do here. It seems like we're calling, well, we're standard moving this thing, and then I guess calling it. And that's going to give us the maybe value. And if we, I guess this is checking like, do we already have it? If not, compute it. And then if we do already have it, return it. So that's just some lazy wrapper, it looks like. Permutation util. Returns true if a permutation is a permutation of the integers, 0 to permutation size. So you pass it in some abscale span, and it, what is permutation.size? Oh, permutation is the thing we're passing in. So if you pass in an array like 167, 2, that's not a permutation of 0, 1, 2, so that would return false. But if I pass in 1, 2, 0, that is a permutation of 0 to 2, and so that would return true. All right, and so we have this, what is this? Permute is a function which takes in an input container thing, something in a container, and a permutation, which is a span. And it's presumably going to do the permutation, applies permutation on input, and returns the permuted array. We check some, we have these macros to check equality. I think these only run in debug mode, but I'm not positive. We check that it's a permutation. We create a vector for the output of the appropriate size. Then we iterate over the permutation elements. That gives us a bunch of indices. And we set the output at index I to be the data at the permutation of I and return the output. So that does compute the permutation. Permute inverse applies the inverse permutation. And we just do that by having permutation on the left side instead of the right side. And it never really occurred to me how to implement a permutation, but this is it's much easier than I thought it would be. Okay, so those are permutations. Here's the C file. What else is there to do? I guess more stuff to implement. Protobuf util. This might not be interesting. There's like, are these two protobufs equal, et cetera, et cetera. We'll ignore that. Shape. I wasn't sure what shape is, but let's find out. The shape describes the number of dimensions in an array. Okay, so it's the shape of an array. That should be familiar from people, I think, from doing Python, like pandas. I think you have to occasionally handle array shapes, possibly also NumPy. And that is array, is tuple, is token opaque, is integer, and so on and so forth. This is kind of like pandas-y stuff, but in C++, and we're going to ignore it. Shape layout will ignore shape tree. Should be a tree of shapes. We have this index table create entry. We pass in a shape. I don't really know what this is about. Oh, I opened up the header elsewhere. Header will tell us, I think. Google's pretty good about giving documentation in the form of comments. A shape tree, here we go, is a recursive data structure which mirrors the structure of an XLA shape and holds a value of type T for each subshape, i.e. tuple or array in the shape. For array shapes, a shape tree trivially holds a single value of type T. For tuple shapes, which can be an arbitrary tree with arrays at the leaves, a shape tree is an identically structured tree with data elements of type T at every node, i.e. the root is a tuple by definition. All interior nodes are also tuples, and all leaves are arrays. Like the shape data structure, this is a tree, and tuple elements cannot be duplicated. All right, that tells us what a tree is. That was useful. I don't know what it's used for, but it's probably used for some computing stuff. We'll try to dig more into what actually XLA is doing. Here's some sharding stuff. You just have encode attributes and parse attributes. String of sharding, auto manual conversion to custom ops. So maybe this is just the sharding string or something, like sharding key. Status should mainly be, we have absol OK and absol status. That's absolutely. Here's status or. This should be just absol stuff. XLA framework.h. We've got a bunch of MLIR stuff, and we're just kind of including some stuff. So we'll plow along. I'm trying to close these files so I can start over from the root directory and try to dig down and find out more about the optimization. This file seems to have nothing really of interest. Here's HLO evaluator. This is now closer to the generation of intermediate representation. So this might be interesting. We'll look at this. This is long. I don't know if we can look at all of this. Let's maybe look a little bit at, actually, let's look at the header. And then we may look at a couple of the C files. And then, because I'm not sure that this is the most coolest thing to look at, well, after looking at the header and like just a snippet of the C files, we'll go back and see if we can find something that's informative and maybe also less long. So Linux 48 is saying, I think you want shape changes to not require any modification of the data. So you have some sort of shape checker which maps indices to the data. That's exactly right. You don't have to copy stuff around. All right, so here's the HLO evaluator header file. We've got parsed static while loop. Represents a parsed static while loop. We normalize the loop representation so that it starts from the induction var init value and increments by step size until it exceeds or goes below loop bound. So you've got a trip count number of iterations to be executed, induction variable index, etc., step size and loop bound. And then parsed while loop, we have this HLO evaluator is a class which extends conf DFS HLO visitor with default. So we're presumably using the visitor pattern, which would make sense. We've got this void function, virtual void on evaluate computation, taking in a computation, enables subclasses to be notified when a new computation is being evaluated. And then we have this evaluate function, which is going to return an absol status or a literal. And we don't know what a literal is yet. Evaluates an HLO module and an array of pointers to literals, returns the evaluated result as a literal if successful. Precondition, the indices of arg literals correspond to the parameter number of the HLO parameters in the computation. So these are just the arguments of the computations. You have to have the same amount. See comment below, for example. Okay, so evaluate is going to take a module, the argument literals, and we're going to call it just evaluate. Where is that? I don't know. Maybe this is the template version. And the template version has some dummy type name set to void. Dummy template arg is to reduce the overloading priority of one overload so that evaluate module on this resolves ambiguously. Okay. All right, that's fine. This looks promising here. Evaluates an HLO computation in array and an array of pointers to literals. Returns the evaluated result, blah, blah, blah. We already saw that. For the following graph, we have parameter 1, parameter 0, and some constant. Where parameter 0 has parameter number 0 and parameter 1 has parameter number 1 in this computation. The input literals array will then have its first literal map to parameter 0 and the second map to parameter 1. I don't know what this constant is doing. But at any rate, we are going to do what? We're going to iterate over the literals and push them back into the arg literal pointers. and then and then call some other version of evaluate. And I guess we're in the header file, so evaluate must be might be in the C file. Here's evaluate internal. This might be the thing that's ultimately called. Evaluates the given instruction and stores the evaluation result in the evaluated underscore map. When a non-empty shape index is given, the instruction may be partially evaluated at the given shape index, and the rest of the result could be marked as undetermined unless it has been previously evaluated using evaluate internal. Such partial evaluations reduces the computation and memory overhead in cases where we only need one tuple element by avoiding the evaluation of a full tuple. All right, so we've got some optimization here, including partial evaluation. It seems like possibly a little bit lazy. And we could maybe start looking at the C. Let's look at the C function. Let's look at evaluate internal. Okay. So if we're already evaluated on the instruction, so we're passing an instruction in a shape index. If we've already evaluated the instruction with the given shape index, we return OK status because this internal function is just populating an internal data structure. So we don't need to return the data structure. We just need to say that we're done. The data structure is ready. If we're not recursively evaluating the operands, and some other stuff is happening, that will return errors. Otherwise, if we look at the instruction opcode, so now we know instructions have an opcode, and it might be k get tuple element, in which case we do some shape index stuff. We push the instruction tuple index onto the new shape index thingy, and then we return of error, calling evaluate internal on the instruction operand of 0 and the new shape index. So this is recursive, and saying that we recursively want to do something. This is a recursive call to evaluate internal. We have, I guess, some kind of like stack machine, and this is, we're saying we want to get the tuple element, and this is, I guess, the instruction to actually get the tuple element somehow. And we have other opcodes like k-tuple, k-parameter. And so we're now in the land of opcodes, which is not so informative since we don't really know, or at least I don't really know what HLO is about yet. Here's an example. I'm not sure if this is... So this tutorial and the code in this directory shows how to write a simple StableHLO program and then compile it with XLA. The purpose is simply to test how XLA can ingest a StableHLO program and produce an executable that's compatible with the local device. As such, the program is a very simple alpha x plus AY, AXPY. Okay. So we'll define a computation AXPY as a StableHLO program using an MLIR file and a StableHLO dialect. It can be helpful to consider the computation as a graph where each node is an operation, an op or HLO, which means high-level operation, and the graph edges are data flow between operations. So we have alpha, which is a float 32. We're going to call multiply 4x 432, 4x, I don't know why. And then we have x, which is 4x 432. And then we're going to add it to y, which is 4x 432. So 4x f32. I don't know. I don't know what so how alpha, x, and y differ. And here's how we define the programming using MLIR in the StableHLO dialect. So we have this func main. Alpha is a tensor of float 32s. %x, I guess percent is the variable indicating something is variable, has type 4x f32. Oh, so I guess this is a scalar. This is a 4-vector of floats, and this is a 4 vector of floats, I guess is what it's saying. And the output is going to be a 4 vector of floats. So that all that checks out, assuming those assumptions hold. And then we're going to StableHLO broadcast in dimension alpha. I don't know what dims equals empty list is. And this is going to return a, what? Is this saying it's going to return a function from F32 to 4x F32? I think this is saying, or no, it's broadcast in dimension, I think, is just taking alpha and creating a an element of R4, a 4-sized array, where each entry is alpha. It's like a diagonal map from this scalar space to the space of 4 tuples. And then we're going to multiply %0 with %x. %0 is this thing. That's the 4 copies of alpha. %x is the x we passed in. And this has type tensor 4 by 4 float 32s. And then %2 will be set to be equal to the addition of %1, which is alpha times x here, and %y, which is the other thing we passed in here. That output will be a 4 by float 32, and we will return %2, which is a 4 by float 32. Okay, so all that makes sense to me. And this is in the MLIR file, which I think I already opened. So let's reverse those two. Note, StableHLO expresses broadcasting explicitly. So we used this broadcast in dimension to broadcast our scalar to a rank 1 tensor, which I think is what I was saying. I'll get to this question in just about a few minutes. And then compile the StableHLO program. We set up a PJRT stream executor client that allows us to compile our StableHLO program. So we have this local client or die. Okay, so we're going to try to get platform CPU, TF, assert OK and assign. So this is some googly TensorFlow thing that is saying we're going to assign the output of this to this. And if it fails, we will fail an assertion, I think, and just probably exit with an error code. But if we're down here, we pass, and we've got the stream executor config. The config ordinal is 0. I don't know what that means. We're going to try to get the executor from the config, set that to the stream executor, and die if that doesn't work. We'll try to get the device state, local device state, and PJRT stream executor device describes the state of a device which can do computation or transfer buffers. Could represent a GPU or accelerator, but we'll use the CPU for this example. And so we have this unique pointer of local device state, which has an executor, a local client, local device state k-synchronous, I guess as opposed to asynchronous, only 32 computations max in flight at a time. Allow reuse is false, and we're not using a callback stream. And then that's the device state, and then we create a device, I guess on 0, maybe CPU 0, or maybe this is just device 0. We're giving it the device state. We're calling it CPU. I don't know if this is an arbitrary string that we're labeling or if it has to be CPU or GPU or something. And then we're creating a vector of devices and emplacing the device on it. So we're just adding the device to the vector or array of devices. And then we have this executor client, I guess, in CPU mode, passing in the local client, moving the devices. The process index is 0. The allocator is a null pointer. Maybe that just means use the default allocator. Host memory allocator is also a null pointer. Should stage host to device transfers is false. I don't know what that means. And the GPU run options is null because I guess we're not a GPU. Then we read the StableHLO program from our MLIR file into a string. So we're just reading this MLIR file into the program string and saying that's okay, or rather verifying that it's okay. And in order to parse the StableHLO program, we must first register the appropriate MLIR dialects. So which dialects, I'm not sure. I guess we'll register them all. This is just func and StableHLO. And then we, I don't know if this is register all dialects that exist, or if this is like find the dialects that we need and register them all. I'm not sure. But it seems like we're not telling it anything about our MLO file. So this seems like it should be, oh, no. We're building a registry that just has func. And it says StableHLO, but maybe that's implied. So then we parse the StableHLO program by taking the dialects, making a unique pointer to it. And then the program is going to be gotten by calling MLIR parse source string with module op on the program string, and then I guess the context being this thing. Now that we've set up our client and parsed our StableHLO program, we can compile it to an executable. And so we'll call assert okay and assign on this compile, which gives us an executable. And now we can execute the program. Finally, in a stable compile test, we can feed the executable some inputs, etc. So is there like a main function? So we got this executable, and we're going to give it some stuff. So create R0 float. This is the thing that was called alpha. This is 3.14. It's basically pi. And then X is 1, 2, 3, 4, and Y is 10.5, 20.5, 30.5, 40.5. We get the PJRT device, which I think is probably the thing we said before. Transfer our literals to buffers. Buffer from host literal. Setting alpha, X, and Y, do the computation. And we get that. We have this buffer for a result. We have this executable object. We're calling execute on it. And we're passing in the appropriate things, alpha, X, and Y. And where's the result? We're calling assert okay and assign result. So we're assigning to this variable here. And then we're going to convert the result buffer back to literal by calling what? To literal sync. I don't know what sync is. Maybe maybe synchronous, as in like not asynchronous. And then check to make sure that our results match what we expect. So we're going to expect that, I don't know what R1 is, but we're going to expect that we're close to this result. And with the error spec of 0.01 as a float. Okay, so that's actually pretty readable, but looks super tedious. We'll take a look at the MLIR code and the other thing and just verify that they are the same as what was in the tutorial. Excuse me, I said I would get to your question in a bit. What's with all the alarms? Should I focus on market trends, or should I focus on one thing and complete it from start to end? Because market is so volatile. Sometimes web dev is on hype. Sometimes AIML. And I see. I think that if you focus on market trends, you're going to get pushed around by the market. So you have to find some sort of home base of like some evergreen skill set that you want to invest in, and then be aware enough of the market so that you don't get left behind. But I don't know. unfortunately, the answer is it kind of has to be a balance. Although completing things from start to end is useful. So I guess I would err on that side over following the market. So this is the stuff we just saw, this MLIR stuff. I guess I feel like I'm about to go, but I want to know this StableHLO stuff. I don't know how. Like, is it? So let me think this through. So we have MLIR and StableHLO, and both are used in this case. They describe this MLIR stuff as being in the StableHLO dialect. And then, so somehow those are related. I think MLIR is divided into dialects. Now that I think about it, dialects. This section contains documentation for core and contributed dialects available to the MLIR repository. So we have ACC, Affine, AMD GPU, AMX, GPU, Func, emit-C, OMP, Shape. Is HLO one of them? So I think they said Func was the thing that we were importing, right? Func. The dialect contains operations surrounding higher order function abstractions such as calls. Func, call indirect, func constant, func return. Is that what we called? The func dialect. And what did we call on func? Func.return. Okay. And then, so how are these related? StableHLO and MLIR. Backward compatible ML compute. So OpenXLA seems to be in charge of the StableHLO repo. It's an operation set for high-level operations on machine learning models. Essentially, it's a portable layer between different ML frameworks and ML compilers. ML frameworks that produce StableHLO programs are compatible with ML compilers that consume StableHLO programs. So you have some framework, like your framework might be TensorFlow or whatever the new one is, JXA or something. No, JAX? JAX. Okay, and that's going to, I guess, compile essentially down to some format or export some format, in particular StableHLO. And then the compiler is going to input StableHLO, which makes it sound like an intermediate representation of its own. Let's ask Gemini, since Gemini is a Google thing. Maybe it will have some understanding of the relationships. How are StableHLO and MLIR related? And how are they different? Thanks, Linux 48. So MLIR is a compiler infrastructure for machine learning that provides a way to represent computations at different levels of abstraction. It's like a common language for ML programs. StableHLO builds on top of MLIR. So it sounds like StableHLO has MLIR as a dependency. It's higher in the stack, you might say. It's a specific dialect within MLIR that focuses on high-level operations used in ML models. Think of it as a special vocabulary within MLIR specifically designed for ML tasks. And it's an extension. Imagine MLIR as a big toolbox with various tools for different programming tasks. And StableHLO is a specific set of tools within that toolbox designed for building and working with ML models. So imagine I'm a car mechanic. Explain it to me in a car metaphor. Grease monkey. MLIR is a giant universal repair manual. It's got schematics for all kinds of engines, foreign and domestic, how the parts fit together, how the fuel flows, the whole 9 yards. But that manual doesn't tell you exactly how to fix things. That's where StableHLO comes in. It's like a specialized toolkit for high performance engines. It uses the knowledge from the MLIR manual, but focuses on the specific tools and techniques used to tune up a racing car. so then we start going into Russian. Klapani, valves. Yeah, very manual. Okay. Cool. That was actually more helpful than I thought it might be. Thanks, Gemini. All right. So I think that's really all I can get out of XLA without not really knowing what I'm doing. Although, what is that PJTR thing? Did I close the tutorial or is it in this tab? I want to know about this PJ thing. Was it PJ? PR? PJRT. Pretty much just another runtime. I'm guessing this is a specifically XLA thing. There's JAX. There's TensorFlow. PGR runtime. The PyTorch/XLA is migrated from the TensorFlow-based XRT runtime to the PJRT runtime used by JAX. So I guess it's the runtime used in JAX for something. I don't know if it's for TensorFlow or for the hardware. Let's ask the AIs. Well, let's ask the search engines first. New TPU runtime. Okay, I'll just ask this thing. What is the PJRT runtime? Nope. No. Platform agnostic runtime. It can be thought of as a translator and mechanic in the. I think it's still thinks I'm a car mechanic. Pluggable, no. Let's try one more time. What is pretty? It's just pretty much just another runtime, right? So in XLA, in machine learning, what is the PJRT runtime that seems to be associated with XLA? It does not stand for that, I'm pretty sure. It's a runtime system designed to simplify how machine learning frameworks like PyTorch and JAX interact with different hardware accelerators, specifically those focused on machine learning tasks. Here's a breakdown of PJRT's role in the XLA ecosystem. So the XLA is TensorFlow's compiler, according to Gemini. I think that's not quite true. That might be really close to true. I don't know. It's a compiler that translates machine learning models into a format that can be efficiently executed on various hardware. I have been assuming that XLA supports, and it seems to support, I think, anything that can output StableHLO. Maybe that is in practice just just TensorFlow, although we did see that PyTorch has an XLA backend or whatever. So it seems like PyTorch can do XLA too. And then the PJRT runtime acts as an intermediary between XLA and the target hardware, like TPUs and GPUs. It provides a common set of functions, API for XLA to interact with the hardware, regardless of the specific hardware type. This allows XLA compiled modules to run on different hardware platforms with minimal changes. Okay. So this is, I guess, kind of like an XLA runtime. It takes in XLA software-y stuff and on the one side, and then interacts with the hardware-y stuff on the other side. Okay. So I think I'm going to leave it at that. Although I will ask, do you use XLA? Me, Bard, I am a large language model, and my core functionality centers around understanding and responding to the language. However, there's a chance that the underlying infrastructure I run on might leverage XLA for specific tasks. Google AI offers various tools and libraries, and some of them might use XLA for optimizing purposes. I'll ask, do you run on TPUs? Yes, I do run on TPUs. They're custom designed by Google specifically for accelerated machine learning, blah, blah, blah. Say, do you like TPUs? All right, that's good enough for me. All right, so that's XLA. I think that's the first kind of deepish dive that we've done into machine learning, if I'm remembering correctly. I think we're going to do more machine learning stuff. This is, as I've mentioned, I think at the beginning and probably several times in the middle there. I'm really generally unfamiliar with the hardware side. And although I understand math, I'm not really super up to date on the software side either. So I'm not really anything like an expert in the machine learning stuff. But I think as we kind of go along, we'll develop a sense of where things are, like what are the performance bottlenecks, which things work really well. And so I think as we go, we'll kind of collectively develop a little bit of expertise. I would recommend TinyGrad. Is H100s the NVIDIA one? Very readable, implements Python, CUDA, PTX. I will look up TinyGrad before I go. Let's look up on GitHub. Linux 48, if you are not on the Discord server, I recommend joining the Discord server, and there is a Google Sheet that has the videos people have been suggesting. There's a separate list, which is the list that I've promised people I would get to, of which XLA was one. And I'm trying to plow through that backlog. And then after that is when I'll start possibly getting to stuff on the list. So right now I'm just asking people to put recommendations on a list, but I'm not promising that I'll get to any of them at all in the future. It's more of just a suggestion. But something that's small like this and readable is certainly something I would very much consider. So thanks to everyone on the chat, and thanks for watching. I'll be back tomorrow.